what we've seen for the stationary waves is that whenever two waves of equal frequency and equal amplitude, they overlap onto each other coming in from opposite direction, and they are polarized in the same plane, which is also necessary so that they actually interfere with each other. They will interfere with each other in such a way that certain locations of the medium would undergo maximum amplitude, which are called the antinode locations, and certain locations of the medium would always appear to be stationary, which are called the nodes. All the particles between two nodes move synchronously, which means whenever all the particles within a loop, they are going up, they are all going up at the same time. And when they're falling down, they're all falling down at the same time. Whenever they are at equilibrium, all of them are at equilibrium at the same time. They have different velocities. I mean, they have different speeds, to be more accurate, but they're all moving downwards when they're at the equilibrium, or they're all moving up when they're at the equilibrium. Their motion is perfectly synchronized. That's why, unlike progressive wave, within a stationary wave, all the particles within one node, they are defined to be at phase with each other. The phase difference between any two particles within a loop or between two node positions is 0 degree because their motion is synchronized. They have different values of amplitude, they have different values of displacement, they have different values of speed, but their motions are perfectly synchronized. They are all moving in the same alignment, in the same direction at any given time. Whenever one of them comes stop, everyone is stopped. Whenever they are at maximum speed, all of them are at maximum speed, something like that. And so what I just mentioned over here is that if we try to represent the structure of a stationary wave in this manner, this is one of the very common ways to represent the structure of a stationary wave. We can draw a wave and then try to draw a dotted structure to represent the other position of the wave. These sizes of the loops are supposed to be equal. It's just a hand-drawn figure, that's why it's not apparent to be equal. So what is important for this stationary wave to actually happen is that we might actually prefer, I mean, this is the type of stationary, so in this stationary wave, all of these particles have a phase angle, phase difference of 0 degree with themselves. All of these particles have a phase angle difference among themselves, which is also 0 degree. But all the particles over here, let's say all of these rectangle particles have a 180 degree phase difference with these particles, let's say with the circle particles, because whenever they are coming down, they are going up, and so on and so on, vice versa. This is the segment that I usually refer to as a loop, which is basically lambda by 2, and this whole part is 1 lambda. That is basically 2 loops. It gives us 1 lambda. And also one more thing is important for us to understand is that if we have this shape, one more thing that is pretty important is that for any wave, this equation is always applicable, v equals to f lambda. This is a pretty important equation. Couple of few things that I need you to understand is that v is the speed of the wave, which is a medium dependent factor. The speed of the wave is typically a medium dependent factor. Medium dependent factor means, if you recall from your O levels, sound waves travel fastest in solid medium, slightly slowly in liquid, and the slowest in gas. Now, why is that? Because the propagation of vibration for sound waves from one particle to another particle is largely dependent on how closely packed the medium particles are. If the gap between the particles are pretty small, then the vibration can travel on really fast, and vice versa. So what goes on with saying that, so one of the measured value that I can tell you is that at 0 degrees Celsius and regular humidity, the speed of sound through air is nearly 336 meter per second, about. This is not exact, but round off. This is the speed of sound at 0 degrees Celsius. Now, what this essentially means is that if you try to produce, so this is actually the speed of the sound at this temperature, which is temperature plays a big role because faster temperature can change the speed of the sound. What is important is that no matter what frequency do we use to produce a certain sound at this level, irrespective of the source's frequency, like 10 hertz, 12 hertz, 100 hertz, 1 million hertz, doesn't matter. Irrespective of the frequency of the source, the speed of the sound through this air would always go at 336 meters per second. If the frequency of the source is high, then we're gonna have a small wavelength. So we're gonna have too many waves produced every second. So let's say the waves are gonna be really uh, close to each other. Wavelengths are gonna be really close to each other. If we have a low frequency, we might as well have a large wavelength. So we might have fewer wavelengths. But in every 1 second time, both of these sound waves will be covering a total distance of 336 meters. That's how, that's the information that I'm trying to get in your head, is that for any wave, whenever there is medium present, the speed of the wave is a factor that is determined by the property of the medium itself. Frequency, on the other hand, the second variable of this equation, frequency on the other hand is not dependent on the wave. Rather, wave depends on the frequency. Frequency of a wave is basically the frequency of the source from which the wave was created in the first place. So if the source vibrates faster, you will have a high frequency sound. If the source vibrates slowly, you'll have a low frequency sound. And lambda is basically the final output which comes from the combination of these two factors. So lambda is basically the uh, variable which has nothing to do for its own. It is the most dependent variable of this equation. V is the independent variable relying on the medium. F is the independent variable which relies on the source. Lambda is an outcome of V and F. So what is important is that for any specific medium, if our speed is constant, then f and lambda would be inversely proportional. If we want to keep the frequency constant, and v and lambda can be vary. For example, let's say if we vibrate the same tuning fork into different medium, for example, air of different temperature, that can be one example. Or let's say we have 100 hertz of tuning fork, we're gonna make a sound in air, then we're gonna try to make a sound in water, and we're going to try to make sound in, let's say, oil or glycerin, some sort of, we can change the medium, physical medium, and try to measure the lambda to all of this medium with appropriate apparatus, of course, but we can do that. So we can change, so if we keep the frequency constant, then v and lambda would be directly proportional, which means they would be directly proportional. So bigger speed of the wave gives you bigger lambda, and so on and so forth. Why am I telling you this? The reason is that whenever we are going to try to produce a stationary wave, we are not going to be able to produce good stationary wave or perfect stationary wave for any random amount of frequency. This is not going to usually work out. If I give you a little bit of explanation, let's say this is a piece of wire, this is a piece of guitar string, or let's say a normal wire that is tightly wound across these two lines. Let's say the length of this wire is L, and in this case, if we want to produce the vibration of stationary wave in this thing, if you try to understand, have a look at the structure of the stationary wave. This is the structure of the stationary wave. I'm just using the word structure because I'll take reference from this figure. What you can see is that, important part is that if we have a string which is tightly wound on its two sides, it is important that these two sides will always be our nodes, because these two sides are perfectly attached to two fixed support ends, like a guitar string, or you can think of like the wire that we use for the Young's modulus experiment, something like that. So the two endpoints are supported in fixed positions. So these 2 points are bound to be nodes because they cannot physically move. They are actually stuck in position. These will be nodes for sure. So what are the likely segments of this structure could we possibly accommodate here? Try to understand that. We have to think of it in a much expanded, or maybe in a bit more squashed view, but I'm talking about how much part of a stationary wave can we logically accommodate within this part. So here's the deal. For this whole structure, if you can see that this is one node position, this is another node position. So we might as well accommodate this part. This is possible. This much is possible for us to accommodate within this part. This will be a bit long, so we have to horizontally expand it. So we're going to have a loop that is really, long in length, but maybe quite squashed in height. That's possible. Or that's step number one. So whatever that lambda is, actually, let me complete this one. So let's say this is the loop that we can produce for this much length of the wire, and in this case, this L equals to lambda by 2. So whatever the lambda that we're developing over here, this length of the wire is equals to lambda by 2. So in this case, we can get that lambda equals to, let me move this a little bit to the right. So in this case, we can get that lambda equals to twice L, which gives us the frequency V by 2L. This is the frequency that we typically call the fundamental frequency, or we can label this as F1. This is what we call the fundamental frequency. Why do you think we call this fundamental frequency? I'll come to that back to that after a while. So it was axis equation. The next thing that we could possibly accommodate within this same, okay, so this is one single sound that we produce, which had a frequency of V by 2L, this much value, which we label as F1. Let's say we now stop the string, and now we're going to try to produce another stationary wave into this exact same piece of wire, but at a higher value. So we want this same piece of wire to give us a sound of frequency that has higher value than this first frequency that I just showed. So if we want to increase the frequency, we have to reduce the wavelength, which means within the same length of wire, we have to accommodate bigger lambda. So because we are going to, because F would be a constant, sorry, my bad, V will be a constant. How fast the wave can travel through this string will be a constant. So if we are trying to increase the frequency, necessarily the wavelength has to become smaller. So within the same amount of length, we have to accommodate a smaller lambda. Now, once again, logic comes into play is that these two ends would be perfectly fixed ends. So we can only accommodate certain segment of this stationary wave in such a way that there will be only nodes on the two opposite sides of this thing. The first example that we picked up over here was this much. The second example that you can pick up is from here to through here, because if we take any other segment, we are not going to have two nodes on the two sides. So we want to take a segment from here and place it over here in such a way so that we can have two nodes on its two sides, and that's why I'm picking up this much shape. So if I try to draw it over here, let's say let me give a halfway mark and then try to draw that loop, maybe something like this. So this lambda will be definitely different than this one. So I'm not going to use that same lambda sign over here. Let's say I'm going to write over here that, let's say in this case, the same length of the wire is used for one full lambda. So I'm going to use lambda prime because I'm using a different lambda over here. So what is happening? Now we are producing two loops over the same length of the wire. So we have one node over here, one node over here, and one node over here. And logically, we have produced two antinodes in between. So this is lambda equals L equals to lambda. So this would give us lambda prime equals to L. So if we now try to get the possible frequency, let's say this is F prime of this setup, this can be given by V divided by lambda prime. Now comes the point, we want to find out that what fraction of this frequency is to this one. Have a look. Lambda prime equals to only L. So I can write this equation, take a good look at what is happening to this equation, understand the working here. V divided by L. To make sure that I get this exact ratio, this much over here, I'm going to do some redundant mathematics over here. So that would be, I'm going to give a 2 in front, so that inside the bracket I can give divided by 12. Have a look. I have given a 2 in front, and so that I can have this exit ratio over here. So what this gives me is twice f1, which typically is called the second harmonic, or it has the double the frequency compared to the first sound. So if this sound has a frequency of, let's say, 50 hertz, this sound would have a frequency of exactly 100 hertz. The reason is very simple. In this case, the lambda has been exactly halved. If you wonder how did the lambda become half, this is what I want you to understand. I'm going to overwrite onto this writing, but to make sense. For the first scenario, whenever we only had one loop across these two stationary points, this was half wavelength, which means the entire original wavelength was supposed to be how much long? If I just try to draw another color, uh, let's say, let me choose red. So if I try to, in our head, this is not physically available, but how much would one full lambda look like for this setup? One entire wavelength might as well look like this much, because two loops make one lambda. So this was the entire length of lambda for our first setup. And in the second setup, these lambdas has become exactly half of that. The entire thing has squashed down to half. So that's what's happening. What the next thing that we can do, I'm going through, I'm going to show you two more steps to convince you of the pattern that we're developing here. Let's say now once again we have the wire which was now not producing any sound stationary. We want to have a higher frequency, with the logic in our head that we must have nodes on the two opposite sides of this string wire. So in this case, what we can do is we can take parts from this structure, which covers three loops on the side. So we can start from here, from the very left, and we can take three loops over here and try to accommodate this much shape over here. So to be able to do that, one logical thing that I can try to do is that I can try to divide this line into approximately 3 equal spaces and draw up 3 loops over here. That way I have nodes on the two opposite sides, and I also have, these are turning it out to be a bit cornered, but they're not supposed to, like, they're supposed to be round. So you can try to draw them roughly with freehand. Uh, this is not the best shape. That's what I'm trying to infer. So, but what I'm trying to achieve, that there are nodes on two sides. We have two nodes in between and three antinodes in between as well. So these high amplitude points represent the antinode positions. How much of lambda is accommodated over here? Let's say this new lambda that is operated over here, because you should be seeing that here we had only one loop, so we had a huge lambda. Here we had two loops, so lambda got a bit smaller. Now we have three loops, so lambda should become even smaller, so that we have even bigger frequency. So I'm going to represent this lambda over here as, let's say, lambda double prime, so which I'm going to write over here. But you can see over here there are three loops, which means this much is, let's say, lambda double prime by 2. This much, one loop equals to half of the lambda for any stationary wave. This much is another one, so lambda double prime by 2. This one is another one, lambda double prime by 2. So altogether, within this much same length of the wire, we have 3 lambda by 2. So I can write this down: 3 multiplied by lambda prime double prime divided by 2. I'm using double prime to represent that this is different from all the other earlier lambdas. This is not the same value. This is different because it is smaller. The earlier values were much bigger. So we have now 3 lambdas over here. So let me keep this in this fashion. And now if I subject lambda double prime from this equation, let's say I can write 2 goes over here, 3 goes at the bottom, so I can write 2L by 3. So let's keep it up over here. And if I now try to calculate the frequency of this sound wave, let's say I'm going to give that with the double prime, F double prime can be given by V frequency equals to speed divided by wavelength. And now I'm going to replace these values. So this would be V divided by 2L by 3. If I take the 3 out, I'm going to get 3 multiplied by V by 2L. So what I'm going to left with is 3 times the frequency of fundamental frequency, which gives me this new the 3 times the frequency of fundamental frequency, and this is usually called the third harmonic. So try to understand what is happening. What I'm trying to convince you about is that whenever we have a fixed length of wire, we cannot produce stationary wave in this wire at any random frequencies. This is the part, this is the primary takeaway from this discussion. Any random frequency will not be produced, will not be able to produce stationary wave within this wave. Why do we want stationary wave in a musical instrument, for example? It's because whenever you produce a progressive wave, you have a certain amount of amplitude. But if you can somehow produce a stationary wave, at the anterior position, the amplitudes become double. Whenever the amplitudes become double, you essentially have a much higher intensity of sound, which means your musical instrument starts to have a much increased volume, which can be heard from much longer distance. So that basically what makes normal acoustic instruments sound so good, because whenever we plug a string in guitar, or we both wire in a cello or in a violin, we essentially vibrate that string at a very fixed at a certain frequency. That frequency happens to be the stationary wave frequency of that length, which allows us to make a very loud sound. So this is what I'm trying to show you over here. So you see, if we have a fixed length of wire, if we have a fixed length of wire, in that case we cannot we can only produce certain discrete means broken or not continuous, uncontinuous value. We can produce certain discrete values of frequency with this length of wire. For example, let's say if this frequency is 100 hertz, this will the next stationary wave can be produced is 200 hertz. The next stationary wave that can be produced is 300 hertz. You cannot have all the frequencies in between. You cannot have 100 hertz, then 150 hertz, then you cannot have 120 hertz. You cannot have all these values. The value of your frequency will be always going in full multiples of that value. Now, there is a catch. If you want to produce all the in between values of frequencies, there is a thing that you can do. You can change the length of this wire. For example, let's say try to think about it. Let's say if this length of the wire is something, and we want to have a sound with a slightly higher frequency, not exactly double. Let's say this frequency is 100 hertz. So I'm gonna let me write this thing. Let's say this is 100 hertz. So if this frequency is 100 hertz, and if we want a sound of, let's say, 95 hertz, so we want a smaller frequency, which means the lambda so has to be slightly bigger. The lambda has to be slightly bigger. So in that case, this part of the wire needs to be slightly bigger. This is essentially what the people do when they're holding the fret. For example, if this is a guitar, let's say if this is a guitar, let's say this is a guitar. Doesn't look much like a guitar, but consider that this is a guitar. So there are the wires, and there is a hole which makes the sound, and eventually on over the hole this guitars go by, and eventually there is a support system. People hold the guitar strings in some places over here and in some places over here, and then plug the string over here. The only aim to hold up these strings in certain places is to control the length of the string, so that that string at that position can give us an exact certain frequency of sound. Whenever they're going to place their hand close to the close to the hole, then they're going to working with a much smaller length of string, which means they're going to produce a much higher sound, higher frequency. If they are holding it on far too on the left, then they're going to produce a much lower frequency. Then they're going to produce a much lower frequency of sound, because in that case the lambda would be high, so the f would become small. So that's basically how it works. If I could go for the fourth iteration as well, simply put, what I'll be getting is 4f, fourth fundamental f, fourth harmonic as well. So that's the part. এই ক্যালকুলেশনের পার্টটা বুঝা গেছে কিনা সবার? If you have any question, please ask me now. Anyone? Okay, we're gonna take some break for Maghrib prayer. It's 6:12 now, so we'll resume class at around 6:22. We're gonna take 10 minutes for Maghrib prayer break. We'll pause in the class for the time being. Okay, so resume the recording. Any questions so far about this calculation and everything that is to convince you that for a fixed length of wire, we can only have certain values of frequencies produced in that wire to produce stationary waves. We cannot have all the frequencies. We can have step frequencies or discrete values. Discrete means not the continuous, not all of the in between values. We can have full multiples of this thing. This is one type of calculation. I'm going to use the same calculation over here to show another thing without rubbing this off. So I'm going to copy this up and use the same calculation for another thing. So let me show you the next part. We're going to have discussion about windpipes. Windpipes can be of basically two types. We can have both and open windpipes, which are basically like this, both and open. So let me just take off a little bit on the ends. Let's say this is a type of windpipe that we can have, or we can have both side open. For example, typical musical instruments that work all work on this principle. For example, if you think of a flute, whenever a person, the musician blows into the mouth of the flute, and with their fingers they hold up the cover of certain holes, and the last hole that they keep open works as the open end. So these two sides where they are open to the atmosphere, these two sides can have the maximum frequency, a maximum amplitude of vibration. So they can move freely, these two ends. So as a result, for an open end tube, both an open tube, both the open sides can work as antinodes. So what is important for us to understand is that open ends will always be antinodes, and logically we can have nodes in between depending on what we are trying to produce. This is the one type of wind pipe that we're going to work with. This is called both and open. And the other type that we can have is both one end closed. You cannot have both end closed because both end closed would not essentially have any way to for the wind to flow by. So we can have one end closed. For example, let's say if I just rub off one end, so this is a one end closed tube. What happens in one enclosed tube, one and open tube? They both pretty much mean the same thing because that's basically the same property because it only has two ends. The property for one end open tube or one end closed tube is that on the closed end we're gonna always have a node. On the open end we're gonna always have an antinode. I'm gonna come to show you the calculation for this windpipe after a little bit, but currently I'm gonna work with this one. So let's take this one and try to observe what we can make out of this windpipe. So I'm gonna copy this up and let's say I'm gonna place it up over here. Now, what I need you kids to understand, whenever we have a both an open tube or open pipe, we will have antinodes on both sides. So this was our reference shape for the whole. Okay, this was our reference shape for the whole stationary wave. So I'm going to choose certain segments of this stationary wave to accommodate within this windpipe, which is going to have antinodes on both of its sides. So I'm going to take different segments, logically choosing, so that I can have antinodes on both sides. So the first segment that preferably comes in observation is that we can choose this much segment, where we have one antinode on the left and the antinode on the right. So this is basically half of two loops. So there is half loop and there is another half loop. Together they basically make one loop. So the gap from a node to node is lambda by 2. Essentially, the length difference from one antinode to another antinode will also be lambda by 2. Goes without saying. So this thing can be accommodated within this part. So if I try to draw this over here, this figure might as well look something like this. Let me show you. Let's say we're gonna have one node over here, so I'm gonna give a dot over here to represent the node, and this will be a really large two half loops. So what I need every one of you to understand that this part of the wind tunnel is essentially showing lambda by 4, and this part of the windpipe is representing lambda by 4. So together they are making, if I sum these up together they are making a total of lambda by 2. So once again we have lambda by 2 portion of a certain wavelength of a sound accommodated within this windpipe where we have both ends open. This happens to be exactly identical of this calculation. Have a look. In this case also we had this exact thing. So what I can do, other than writing up this whole thing, I'm gonna copy this part and place it beside this one, and this will work just fine. Forget about this red line. These red lines were over here for as a part of the figure, but this same calculation can hold true for this whole pipe as well. The entire length of the windpipe is equal to lambda by 2, so lambda equals to 12. So the fundamental frequency would be f1 v by 12. This is the first thing that we can have. Now if we blow wind within this pipe at a bit higher pressure to produce a much more higher frequency of the sound, we can try to accommodate the next acceptable segment of the stationary wave within the same windpipe. So what I'm going to do, I'm going to copy up this windpipe once again.
Sir, will there always be two waves?
বুঝিনি আবার বলো।
সবসময় কি দুইটা ওয়েভ থাকবে পাইপটার মধ্যে?
এখানে actually we are not going to say we're going to have two different waves. We are going to have two opposite waves will be here. So one wave is going to coming from this and going this way, another wave is going to start from here and going in opposite direction. But because of the length constraint, we can accommodate two loops over here. So if you want to think for in terms of progressive wave, this much would be half lambda of a wave, this much would be another half lambda of a wave. Or if I try to show you the two individual progressive wave that can actually lead to this function, this can look like this. For example, this is just an additional drawing. Let's say if this is the wind tunnel, let's say one progressive wave has an antinode over here. So let's say this wave looks like actually, other than choosing this figure, I could show you some other parts. Drawing this is a bit nightmare for me on this figure. So I can show it to you in a different figure to convince you, to help you convince what I'm trying to show you. So for that part of the wave, we are going to have, let me draw a rectangle just to help you understand. We're going to have this much part within this wave, this much part. So this is actually the section of a wave which is a same section of the medium, but we have different parts in different places. So what we can have, we're going to have an antinode on this side, we're going to have another antinode on this one, and the midpoint is always going to be a node. So this is the part of the segment that we're talking about. So we will definitely having two progressive waves crossing into each other from opposite directions, but the amount of space they are occupying is essentially this much. So we are having node produced exactly at the center. So for example, have a look at this position, this position, this position, this position. Always at the center you are having one node. On the two ends you are having antinodes. So we can achieve this one. This is essentially what is happening for this part of the wave. যাই বুঝছো কি বলছি?
জি স্যার, কিন্তু এটা হচ্ছে দুই সাইড ওপেন না, তাহলে কিন্তু আমরা তো ব্লো করবো এক সাইড দিয়ে একটা ওয়েভ, তাহলে দুই সাইড দিয়ে ওয়েভ কেমনে হচ্ছে?
Yeah, exactly. We're gonna blow in from one side. This vibration is gonna travel through the pipe, and eventually it will be able to vibrate the air particles on the other end as well. And because this part is absolutely open to the atmosphere, these particles can have the maximum amplitude. But all the particles which are trapped inside that closed tube, they cannot have the full amplitude because they do not have the space to make the full vibration. In this case, what I need to understand, we are talking about atmospheric particles, so the vibration will be essentially happening along the length. So these particles can have a much higher amplitude of vibration. These particles will have a much smaller heights of vibration. This end over here usually does not work as a reflector. It does not work as a reflector because this is an open end. This basically works as a secondary source, sort of like a secondary source. So maybe we are blowing in from this end, but this produces a virtual secondary source existing over here. These two sources overlap onto each other, producing the stationary wave. বুঝছো কি বলছি?
জি স্যার।
আচ্ছা। So this is the first scenario for which we could get a stationary wave in a both side open tube. As for the second case, if we want to get a bit higher frequency, we have to choose a bit smaller part of the lambda. So we have to choose a bit bigger segment. So if I now choose logically another segment from this wave that has antinodes on both sides but slightly bigger than this segment, the next logical choice, let me draw it with a red rectangle maybe, can be this much. Have a look at this much rectangle. So what is happening here? Once again we have a node, antinode on the left side, we have another antinode on the right side, but we have this much loop over here. So we have half loop on the left, one full loop at the middle, and another half loop over here. So to be able to draw this figure efficiently over here, I'm going to try to divide this. I'm going to try to divide this whole space into 4 equal spaces. I'll show you why 4 equal spaces. Just give me a moment. So let's say I'm going to give a point at the halfway point. I'm going to give another point over here. I'm going to give another point over here. The reason I'm dividing into 4 equal spaces because I'm trying to accommodate lambda by 4 over here. So if I try and draw, this part can look like this. This is half loop. Then this is another half loop. And this is another half loop. And comes the last half loop. So if you give a close observation over here, how many total loops are there? One full loop at the center, 2 half loops on the 2 sides. So you basically have 2 loops, right? So how much of lambda would we have available in this space? This much part gives you what? Lambda by 4. This much part gives you lambda by 2. I should give lambda prime because we are talking about a different lambda than this one. And this much part gives you lambda by 4. So altogether, how much lambda do we have over here? In the total length of the pipe, how many lambdas do we have?
1.
Add this up all together. So we have exactly lambda. So I can write over here L equals to lambda. And to be honest, lambda prime because this is a different frequency. This is exactly similar to what we had over here. Have a look. So what is essentially happening? I mean, why do I have the math repeating itself? The reason is that in this case, for the where we had fractions of lambda by 2 available. For the largest frequency, for the smallest frequency of sound, for the largest lambda, we had lambda by 2. Then we had lambda, then we had 3 lambda by 2. So the increments are happening in terms of lambda by 2s because we had nodes on the 2 sides and the in-between space was filled logically. In this case, we are having 2 antennas on the 2 sides and we are having the in-between space filled logically. So that's why we are having the same thing happening. So if you try to compare, having 2 nodes on the 2 sides is basically lambda by 2. Having 2 antennas on the 2 sides is also lambda by 2. So these two shapes are basically similar to each other but not same. Only they are shifted by lambda by 4 consideration. So for the string, we are going from node to node and then node to the next node and node to the next node. But for the both an open pipe, we're going from antinode to antinode, then antinode to the what can I say, following antinode, and so on and so forth. So I can copy out this calculation over here as well all together and place it right over. Oops, koi rakhlam eta. I can place this calculation right over here and this will perfectly make sense. In the same way, I can have the third mechanism as well. So if I try to copy this open tube from here, in this case, we're gonna try to accommodate a third harmonic. In this case, so we're gonna try to accommodate a much bigger segment of the stationary wave over here. So the blue rectangle over here was for the first harmonic, red rectangle over here was for the second harmonic, and for the third harmonic, let me draw with, let's say, maybe orange. So we can start from the same point and we're gonna try and go up to this point. So I'm talking about this much segment. So if you now take this much segment and try to squeeze it within this length, we're gonna be producing the third harmonic. Now, drawing this part can prove to be once again a bit trouble, but I need to understand how much of the stationary wave structure are we actually considering to exist here. Have a look. If you consider this orange rectangle, we have half loop on the left, two complete loops at the center, and then another half loop on the right. So drawing this figure within this tunnel can prove to be a bit mess, but I'll help you in the process. We can try to divide up the entire space in between in terms of lambda by. That's exactly what I'm doing for in this figure as well. Here I had 4 lambda by 4. So 1 lambda by 4, 2 lambda by 4, 3 lambda by 4, 4 lambda by 4. That's why I divided this thing into 4 equal segments and do individual lambda by 4s. I want you to count exactly how many lambda by 4s will be available within this orange circle. Do you see the orange circle, or is it difficult to see? Should I give a different color? Maybe ash color would be a better idea, I think, because red and orange can be a bit confusing. Okay, so this ash color rectangle, let's give it a count. So we have half lambda, we have half loop over here, half loop, another half loop. So 1, 2, 3, 4, 5, 6. How many half loops do we have? We have altogether 6 half loops over here. So let's try to divide this in between space into 6 equal spaces so that we can accommodate all of these figures. So dividing this up into 6 equal spaces can also be a bit difficult, but bear with me. Have a look what I'm trying to do. I'm first going to divide into 2 equal spaces, so giving a dot approximately at the middle, and then I'm going to try to divide this space into approximately 3 equal parts. So let's say one goes up over here, and another goes up over here, and same thing over here and over here. So I've given 6 dots over here. I've given multiple dots over here to divide this into 6 segments. 1, 2, 3, 4, 5, 6. Now I can start drawing the figure, and this will take a while, but bear with me. So this is the one part, half loop, and the half loop. That's sort of like it. So what we're having over here is that we're having so if we now count exactly how many fractions of lambdas do we have in this figure. So this part is lambda by 4. So let's say double. I'm gonna give double prime because this is a different frequency lambda. So part 1, 2, 3. I'm writing 2 over here because I'm trying to represent that this part is lambda by 4, quarter of this lambda. This part is another quarter of this lambda. This is the third quarter part, 4, and then 4th and 5th and 6th. So we have 6 lambda by 4. So if you do multiply this 6 into lambda double prime by 4, how much do you get from here? We get 3 by 2. This is the exact amount of length that you got for this figure as well. So these two figures are pretty much similar, except for they are a bit shifted. One was going from node to node, the string, and the pipe is going from antinode to antinode. So once again, I can copy this whole calculation from here. I could actually write this whole thing, but I'm not preferring to write, just to give you the idea that they are exactly same. So this perfectly works. In this case, this entire length of the wire is covering 3 times the lambda double prime of 2, which is a new wavelength fraction. And if I go ahead with down the calculation, the new frequency that we're gonna get is gonna be 3 times the fundamental frequency. So we're calling this the third harmonic. So That's how the whole thing works. So strings and both end closed tubes, both end open tubes behave in similar ways that we can get all the multiples. I'm using the word all because a bit difference will be shown after a while. We can get all the multiples of lambda by all the multiples of fundamental frequency. We can first get the fundamental frequency. Fundamental frequency is basically the smallest frequency you can produce, which happens for the biggest lambda, and then you can have multiples of that frequencies produced depending on the bigger amount of frequency that you try to get. So you can get second harmonic, third harmonic, fourth harmonic, sixth harmonic, fifth harmonic. You can get all the harmonics out of this two equipment. One is the string, and the other one is the both end open tube, because they are capable of accommodating full multiples of lambda by 2 uh, within them. Full multiples of lambda by 2 means for the first segment it was accommodating lambda by 2, then it was accommodating 2 lambda by 2, then it is accommodating 3 lambda by 2. For the this one would be accommodating 4 lambda by 2, 5 lambda by 2, 6 lambda by 2. So it is accommodating full multiples of lambda by 2. So that's what is giving us this whole thing. Lambda by 2 is the key here. So each lambda by 2 is responsible for one set of frequency as per the drawing suggests. The next thing which is left is to discuss about the one end closed tube, which is this one. This is a bit interesting and different from the earlier discussion, because for one end closed tubes, as you can see, that one side would be always antinode, the other side will always be node. So how can we work with this figure properly? Let's give it a try. I'm not going to need that additional discussion anymore, so I can get rid of that part. Let me show you this right over here in this space. I'll have to write new stuff, so I'll be getting rid of this. I might as well need this figure later on, so I'll place it somewhere. Maybe right over here is good. I'm gonna try to show you this one. Okay, all set. Achha. This figure is already a bit clumsy, so I'm gonna take a new figure of the stationary wave structure or standing wave structure to show you what is gonna be happening over here. Let me copy something up from the internet. So maybe copy which figure? Maybe I'm gonna copy this much. Okay. The reason I'm bringing up this figure is just to give you another idea for how we can approach this figure. So let's have a look and try to understand. And if you have any confusion, respond accordingly. We want to accommodate within this windpipe a certain segment of the stationary wave structure so that we can have antinode on the left and node on the right. I could do it the other way around as well. I could keep the node on the left side and antinode on the right side as well. It can work perfectly equally. I'm just choosing this version, but you can have other versions as well. Don't worry about that. I could just rotate this figure by 90 degree, 180 degree, and you would have the same figure. Let's try to find out a segment of this stationary wave over here, which has an antinode on the left, and adjacent to that we have a node. If you take a good look, you'll find out this segment can be this much. I'm talking about only this much. So one node on the left, so one antinode on the left and one node on the right. So we are talking about only this much part of the wave, which happens to be exclusively, I mean, how much is this much length in terms of lambda? If you think in terms of lambda, how much is this much length?
Lambda by 4.
This is exactly lambda by 4. Do you please
Lambda by
understand this
4.
part? It's half of a loop, so lambda by 4. So we have to somehow accommodate this only this much within this whole length. Can prove to be a bit difficult, but we just have to do that. So observe, I'm just trying to do that. Oh, that happened better than I expected. Beautiful. So in this case, the entire length of the tube is covered by lambda by 4. So if I go ahead with the calculation, it gives me lambda equals to 4L. So frequency will be equals to V by lambda. So let's say V divided by 4L. This is defined as first harmonic or fundamental frequency. Let me label this with F1. So that's the first scenario. So the amount of lambda that you are covering in your first scenario is lambda by 4. So what you should understand that pretty much like to the earlier case, the multiples should also happen with respect to this one. For example, in these two figures, we are covering, for the first figure, we are covering lambda by 2, and then we had 2 lambda by 2, which is basically lambda, and then we had 3 lambda by 2, and then we had 4 lambda by 2, so on and so forth. And that much as well happen over here. Lo and behold, this will not happen. Let me tell you why. Try to observe in this structure once again and to figure out 2 points where you have antinode on the left and node on the right. If I try to label this with, let's say, purple or maybe blue, I'm not sure. This is the part of the segment that I'm talking about. Have a look. This is the next part after the lambda by 4, where you have one antinode on the left and one node on the right. This much segment. So I'm talking about this much segment. So in terms of lambda, how much do you have over here for this wave? Is this, I mean, this part is lambda by 4, then this is another lambda by 4, this is another lambda by 4. So how many lambda by 4s do you have here?
1.5. Like,
It has 3 lambda by 4s. Do you understand this part? Can you see it, everyone? This is important that you see it.
Yes, sir.
Sir.
Yes, sir. So I would require, do I have this pipe anywhere? I don't have this pipe anywhere. I should have had a copy of this pipe somewhere. I'm going to copy this pipe anyway. With a bit thicker line, green rectangle, and might as well have used green. So that's one. Let me draw another one because I'm going to need at least 3 to make a pattern and get rid of the open ends. Okay, the thickness is a bit wide, but disregard that. They are supposed to be identical. But logic stays the same. Left side should be antinode, right side should be node, left side should be antinode, should give dots for my convenience, and the right side should be node. This is how it's supposed to work. So for the second part, I'm going to accommodate this much segment over here. So to be able to draw this more efficiently, I'm going to count exactly how many lambda by 4s am I dealing here. I'm dealing with 3 lambda by 4s over here. So I'm going to try and accommodate. I'm going to try to divide this in between space into 3 equal spaces. So let's say here one dot. ওয়ালাইকুম আসসালাম। হ্যাঁ ভাই বসেন একটু ক্লাস নিচ্ছি 1 মিনিট পর। So we're going to divide this into 3 equal spaces, something like that, and we're going to accommodate this part of the drawing right within this space. So it's going to work. Let me try to fill this up maybe with a different color. One. Something like this. This can work out for me. Now, if you observe, in this case, we have a much smaller lambda because this is really small. But in terms of fraction of lambda, we have accommodated 3 times the lambda by 4. So this entire length of the tube is now covered with a new wavelength. Let's say let's name this wavelength double prime. But here we have 3 times of that thing. So this part, this one part is lambda. So double. I should have given double prime. I should have given a single prime. Lambda prime by 4. So this part is lambda prime by 4. This part is lambda prime by 4, and this part is also lambda prime by 4. So these are the 3 parts that we have, lambda by 4s. Now, if I go ahead and do this calculation, what's going to happen? Lambda prime equals to 4L by 3. So the new frequency we're gonna get is V by lambda, which is V divided by 4L by 3. So we get 3 into V by 4L equals to sin got messed up. 3 into 4L, which gives us 3F1. Interesting. Why interesting? You can see that the first within the first figure, the frequency that we got, which was fundamental frequency, in the second possible scenario, where we could have one antinode on one side, open end, and node on the closed end, the next frequency at which the resonance can occur or the stationary wave can happen is 3F1, not 2F1 like earlier. So we are missing the even multiple because of the structure. If you wonder why is that, because like I said, that it's all about how many multiples of the original lambda can you accommodate repeatedly. So in the first segment you could accommodate lambda by 4. In the second scenario you could not accommodate, or we could not accommodate 2 lambda by 4, because that would not be okay, because 2 lambda by 4 would require antinodes on both sides, not allowed. In the next possible scenario, we could accommodate 3 lambda by 4. So because the number of lambda by 4s got increased by a factor of 3, so the actual lambda got reduced by a factor of 3, so the frequency got tripled. So we are missing out the even multiple. Same thing can be achieved for this part as well, which is going to be a segment for 5. So if we now observe this segment once again and try to repeat the same behavior, then we try to draw that with maybe pink. Pink is a good color. So from here, it's this much that we're talking about. We have to accommodate this much part of the wave within this third segment, where we can have one antinode on the left, one node on the right. And if you do give it a count for this pink circle, let me choose right in pink as well, we're gonna have 5 lambda by 4 within this part. So somehow we have to divide this in between space in 5 equal spaces. Can prove to be a bit challenging, but we're gonna do this anyway. So I'm gonna try to divide this into 5 parts in the best way that I can do. This is just by estimation. You can use ruler, be my guest, no problem. And for each of these segments that you can see from here to here, here to here, I'm gonna try to draw half loop. So starting from the antinode, this is one half loop, lambda by 4, another one, another one. I'm showing you the detailed process for how I usually draw this figure, because you will be requiring to draw these shapes in given blank spaces of figure in your actual exam. This is a part of the question, and the drawings actually can happen to have quite a good amount of marks. So being able to draw these lines properly is actually a required skill that you will have to develop over the duration of your course. So over here we have 5 lambda by 4s as actually. So I can actually label, let's say this is 1 lambda double prime by 4, and we have 1 over here. So this is one segment, and then 2, and then 3, and then 4 and 5. So if I go ahead and write up this equation, this is gonna be something like this: 5 lambda double prime by 4, which gives us lambda double prime becoming 4L by 5. So if I now go for the new frequency we're going to develop from this setup, it's going to be V by lambda double prime, which is going to be V by 4L by 5, which would be 5 times V by 4L, which gives us 5F1. So this is the 5 times the frequency of the typical of the fundamental frequency. And we could go on further, but having 3 actually develops the pattern, so I'm not showing you any further. But if you want, you can draw further, and you're gonna get 7, then you're gonna get 9, then you're gonna get 11. So if I zoom out and try to show you a consolidated view of what we just discussed for up till now, is that here you can see that in one end open tube or one end closed tube, they're both the same thing. We can only produce odd multiples of fundamental frequency. You can have the fundamental frequency, then you can have 3 times, you can have 5 times, then you can have 7 times, then you can have 9 times. You cannot have the even multiples. Even multiples are missing. That's how this type of windpipe can work. This is the basic type of windpipe which you can consider like the cap of your pen. If you blow in the cap of your pen where the bottom side is actually closed, not open or not without any hole, it's actually solid closed. This is the type of windpipe. This is what we're talking about. So you can either produce a certain frequency which can be very low. Then if you blow harder, you can produce a second frequency which is a bit higher. And if you blow even harder, you should be able to hear a much higher frequency. I can try to replicate this thing for you, but I'm not sure how pleasant it's gonna be for you to hear over the microphone. Should I try this? Not sure. So this is for the one and closed tube, and for the both and open or the string, they pretty much allow us to have all the frequencies of the scenario. So if you wonder what kind of questions are we going to be having from this part, I'm going to show you some MCQs right after, right within today's lecture, going for this one. But before I go further into this thing, I'd like to have you read one specific experiment. Let me pull that up. I have this in my book. Application booklet, fees, notes. Where is the book? তোমাদের বইটা তো নামাইছ না, বইটা গেল কই?
স্যার আমি পাঠাই দিই, আমার কাছে আছে।
দাও দাও, আমার কাছেও আছে। কই আছে এটা হচ্ছে কথা।
সার্চ বারে খোঁজ করলে আসবে না?
এই যে পাওয়া গেছে। তোমাদের বই হচ্ছে এটা। এটা না তোমাদের বই?
জি স্যার, এটাই।
Yes, sir.
I forget stuffs. Like yes. I would like you to read this experiment, this one. Turn up your book at page number, what is this level page number? 214, this is 226, I think. A boy page number 214, sorry. Turn up this page number 214 and try to read this experiment. You might as well start from box 15.1. Start reading from here, reading this experiment, and go all the way up over here. A question, a tinta page poro. I'll give you 5 minutes of time, and then I'm going to talk about these things. পেজ নাম্বার 213 এ বের করো, এখান থেকে পড়া শুরু করো, পুরোটা পড়ে যাও। হয়তো অনেক কিছু বুঝবা না, যা কিছু না বুঝবা আন্ডারলাইন করে রাখতে, মার্ক করে রাখতে। আইল বি ডিসকাসিং এভরিথিং ফ্রম দিস এক্সপেরিমেন্টস। এই এক্সপেরিমেন্টগুলো থেকে অনেক কোশ্চেন হয়, বিলিভ মি অন দিস ওয়ান। সো ইউ নিড টু হ্যাভ এ গুড আন্ডারস্ট্যান্ডিং অন হ্যান্ডস অন আন্ডারস্ট্যান্ডিং ফর হোয়াট ইজ হ্যাপেনিং হিয়ার। পড়া হয়েছে?
Yes, sir.
অলরাইট, যে যতটুকু পড়ছো একটু পজ করো। This was enough time to read this whole thing because this is mostly pictures. Half the column is all pictures and only half the columns are writing. So if you were reading, it should be over. Anyway, I'll pick up this experiment. So in this experiment, they are showing us that what happens for a vibration generator whenever we are making up a vibration and we are having this thing. This was a certain video that I actually showed you in the earlier case with a person with a teacher actually doing an experiment in front of a white piece of paper. What is important for here is that using the signal generator, we can make this thing is actually a solenoid, and this signal generator produces an AC current, which makes this support system over here. You can see there's a small support thing over here. This can actually make the wire go up and down. How much amplitude does this signal does this vibration generator actually provides to this wire is not the primary thing. What this thing is mostly dependent on is how much frequency is this thing is vibrating. For example, in this case, apparently this thing is connected a bit inside this loop. Have a look. If you observe this loop is actually finished exactly at the end of this picture. This is where the sharp end is. So this is a node position. This is another node position. This supported end is obviously a node position. So this is an antinode exactly at the middle where the amplitude is highest, exactly at the halfway point between two nodes. This is another antinode. This frequency oscillator is placed in such a position so that it can actually provide some vibration to this thing. So this thing might be going up and down at a much smaller amplitude. This really doesn't matter, but this is capable of vibrating the wire at such a frequency that for that frequency that the relevant lambda is shown over here. So whatever the frequency of this vibration generator over here is going up and down by, for this wire, it produces a lambda that has a length from here to here, because this basically is two loops, which means exactly one full lambda. So if we now lower the frequency of this vibration generator, then this lambda will become bigger. And then if you increase the frequency, this lambda will become smaller. For certain values of this frequency generator, full multiples of fundamental frequency, we can have complete loops existing in the entire length. So if you have exactly one loop, that's fundamental frequency. If you have exactly two loops, you have second harmonic. If you have exactly three loops, you have third harmonic, so on and so forth. So that's about this experiment. This scientist actually did this the first time, I think with some mechanical way. So it's named after him. That's not very important, but I just want you to understand what is happening here.
Sir,
Yes?
the vibrator vibrates, but it's still considered a note, right?
No. The vibrator cannot be placed at the node. The vibrator which is introducing vibration to the medium, in this case the string, this cannot be placed at the node. It can be placed anywhere else. It
The
can be
third
placed
line of the right side, row 6, it is a note.
where?
Right side.
এই যে আচ্ছা, so in this case it says that the end attached to the vibrator can only move a small amount. This small amount in this case they are considering as negligible, but you can see it very well in this figure that this is not essentially zero. Zero is happening right over here. The source cannot be placed at the node. This thing information is over here is wrong. Because think logically, you don't have to take my word for granted. Think logically. If we place the vibration source at the node, how would the energy be introduced to the system in the first place? Because the source has to make some oscillation to introduce the vibration, right? Node is the logical position where the vibration of the medium is zero, amplitude of the medium is zero. So we cannot essentially place the source exactly at node. It can be placed pretty close to a node for our visual experience, but it cannot be placed exactly at node. That would not work. Do you get my point?
Yes, sir. Yes, sir.
Sure. Then we have an experiment for the microwave. What we are doing over here, that this is actually this probe over here is actually a detector. We have with a stand a microwave sender. I mean, the reason we're doing some experiment over here with a microwave because microwaves have a frequency in centimeter range. For example, 3 to 5 centimeters, something like that. So over here, we have a signal generator which can produce a certain frequency of microwave, and we have a reflecting sheet over here. This reflecting sheet is basically a very flat sheet of metal because paper or cardboard would not reflect microwave very well. So metal is recommended. So what we're doing over here, that we are going to send waves from here, and eventually this wave is going to get reflected off this reflecting sheet and eventually come back. As a result, for the space in between, we're going to be able to produce a stationary wave. Now, interesting is that if now what I need you to understand very clearly, the source over here must work as an antinode because this is the position where the vibration is getting created for this thing. The reflection part, where the reflection is happening, should be an node because this is where the waves are getting reflected from. So in between this space, we can have multiple different places. So for a specific position of the transmitter for the in between space, we can set up a stationary wave in between. And once we have the stationary wave, if we use this probe to move back and forth along this line, we should be able to detect a high amplitude, then reducing amplitude, 0, and then increasing amplitude, highest amplitude, then once again reducing amplitude and 0. So that variation over here is actually detected by a voltmeter, as it is showing over here. Or it can as well be a galvanometer for all I care. Bigger vibration, bigger amplitude of the electromagnetic wave will give you a bigger amount of flux line cutting or magnetic field line cutting onto this probe, and that will induce a much bigger voltage onto this wire. And places where the amplitude is much less, you would have less cutting, and as a result, your amplitude would be close to 0. So by moving this thing back and forth, we can find out exactly what is the gap between one node to the next node. Think about it. Let's say we're going to move it back and forth. For a specific position, we find out the 0 reading on the meter, which means that position of the probe, this circle, this one represents a node position, because if you have 0 reading, it means there is no vibration. That is the node position. Let's say now we're going to move this thing slowly closer to the source, or we can move it closer to the reflecting plate as well, doesn't matter. We will be seeing that the reading on the meter is slowly increasing. Beyond moving a certain point, it will reach to a maximum. We are not going to take any reading from the maximum because observing the maximum position is actually pretty difficult, because the pin is going to move vigorously back and forth. So we're going to move it further and once again find out the position where the meter reading once again becomes perfectly 0. This new position also determines a position of the node in the structure as well. So we can find out 2 different points within this space. Each of these points represents one node and then the consecutive node, and the gap and the space or the length between 2 consecutive nodes is always lambda by 2. Once you can physically measure this up using the help of a meter rule, multiplying it by 2 can give you the lambda of that microwave frequency, which you might not be able to get from this wave, from this source. And if you now check it with your formula that V equals to F lambda, where V is the speed of microwave, which for vacuum is in 3 to 10 to the 8 meter per second, you can confirm that your experiment actually worked out. So this is one scenario for the microwave experiment. এইটা থেকে আমাদের কোশ্চেন হয়। এরকম সিমিলার একটা এক্সাম্পল, কিছু আরেকটা এক্সাম্পল আছে যেখানে আমরা দুইটা ডিফারেন্ট লাউড স্পিকার ইউজ করি which are operated from the same source, যেটা আমরা ডাবল স্লিট এক্সপেরিমেন্টের জন্য দেখব, পরে আসবে এটা।
স্যার,
Yes.
এখানে ডিসটেন্স মানে ট্রান্সমিটার আর রিফ্লেক্টিং শীটের মধ্যে ডিসটেন্সটাকে আমরা করতে হবে না, মানে how do we know that a stationary wave is being set up? যদি wrong frequency দেওয়া তো হবে না?
One of the ways that we can make sure that the stationary wave is actually set up, that can prove a bit difficult to do, but there is a way. I mean, what I want you to understand is that the way the in-between space is going to be filled up is by having an antinode on the exact source location and a node on the side position. So you're going to be having loop, but at the end you're going to have a half loop. So to have this thing properly placed, what we can do, the mechanical way is that we can place the micrometer transmitter in a certain position, in any random position, and then we we'll keep it in a certain position. We're going to keep everything in a given position, and then we're going to slowly operate this knob to change the frequency of the microwave so that we can get a zero reading on the microwave. Because you have to understand that if we increase the frequency, then the lambda will become smaller, which means you will be having bigger number of loops within the same amount of space. Because bigger frequency makes the lambda smaller, so you'll be having more congested or more compressed wave structure for the same amount of length of physical space. And if we keep on doing that for a certain frequency set on the source, you can have this detector located at a node position. So we are going to try to move this slightly back and forth and also adjust this thing as increasing and decreasing to find out such a position so that where the probe can give us a zero reading. When the probe gives us a perfect zero reading, this is a proof that we have a perfect node created at that position. A perfect node can be only created at this position only if there is loop plus, any number of n plus half loops in between this space. N plus half means integer number plus half loop. So because you'll be having loop, 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 loop from the reflecting sheet all the way to the source, and close to the source, you're going to have one half loop. So the first adjustment is actually done by slight movement of this probe and adjusting this knob simultaneously and continuously observing on the meter whether we get a zero reading over here or not. This is a bit of a trial and error, can take some time, but it is experimentally achievable. বুঝছো কি?
Yes, sir.
It does sound complicated, but did you understand the process, that why are we doing this?
Yes, sir.
Because we cannot essentially see the microwaves, so that's where the detector comes in. The third experiment that we have is that air column closed at one. Yes.
Other experiments, একটা question ছিল, like if we're vibrating the source a little bit, how is it like producing like larger amplitudes in the stream? Like ওটা তো অ্যান্টিনোডের না, source এটা কি বলে? The generator is not as an antinode. Then how are we producing like larger amplitudes? Antinode এটা দিয়ে দিচ্ছি কিভাবে?
Okay, I get your question. Hold up. So you're asking me that if the source is always at antinode, then how does it produce the stationary wave? I mean, how is the stationary wave being produced here? Is that your question?
No, sir. First experiment question.
Yes.
Yes, source is not at the antinode, right? Node কাছে খুব, তাই না?
The source is not at a node.
And not at a node, but very near the node,
It
right?
can be. Yes.
Yeah, but তাহলে আমরা like how is it producing the
Okay, I totally get your point. Okay, I'll tell you this. Let me show you an experimental setup which might make a bit better sense. Have a look. Let's say this is a wall. This is a string. This is a person holding the string. Whenever the string is taut, our brain can actually work as a very good detector mechanism which can detect the frequency of a certain object and can sync up with it. We can do this by our cognitive systems. So if I start to oscillate this wave, a rope, we'll see that a vibration is going down the rope, and from the wall it can reflect back. Pretty soon we'll find out that what is the exact frequency that we need to vibrate this to exactly have one loop. Now here's the deal. To make one full loop, we do not essentially have to move this hand at the antinode position. We don't. We just need to periodically add up energy to the system so that our hand movement is always working in the same direction of the preferred motion of the wave. Let me explain what this means. Let's say for this setup, the frequency of this wire is, let's say, 2 hertz. What does 2 hertz mean? It means it's going to complete 2 cycles every second. So if I want to make the stationary wave or resonance, for example, resonance is basically where multiple waves join together and the energy adds up to give you a much higher amplitude. Resonance is a much bigger topic to discuss for you in A2 levels. It is not very highlighted in AS level, but sometimes the term comes in because it is inherently added within the concept. So the idea of resonance is that whenever we vibrate something, think about it, whenever we vibrate something, if the vibration adds up onto itself over multiple iterations, multiple oscillations, and slowly start to give you a much bigger amplitude of the motion. One of the examples that I can give you is that let's say if you kids don't have meter rules at your disposal, but let's say you have a steel ruler. Let's say you have a steel ruler. Do you kids have a steel ruler? To steel ruler?
Sir.
Many of you might. Okay. Let me show you a very simple experience. Let's say this is the side of a table. Okay, this is the side of a table. Let's say this is your steel ruler. This is your steel ruler, and you are going to hold the steel ruler in this position by your hand. Let me show your hand by, let's say maybe brown, because we are brown people. So let's say you're gonna hold the steel ruler over here, press down onto the table so that it's not gonna move. Using your hand, your other hand, let's say by pressing down over here, let's say by another finger you are pressing down over here. What you're trying to do, your aim is to produce a very large amplitude of motion over here. What you can do is you'll find out that for this position, if you start oscillating this, you'll soon find out that you can press always the ruler in such a way that it can actually give a much really large amplitude of vibration. It's possible. To achieve this, what essentially are we doing? This finger is only capable to apply force downwards. What we are doing to achieve a really high amplitude over here is that every single time this ruler is about to go down, we are pushing it down further. So let's say when the ruler is in this position, the highest position in its bend shape, let's say this is the possible bend shape in the highest position, this is the possible bend shape in the lowest position. So what we're going to do with our finger or this finger, we're going to apply force when the ruler is going down. And as the ruler is coming up, we're not going to apply force anymore. So we're gonna lift our finger by our own muscle as the ruler is going up. So we're not going to oppose the upward motion, but we are going to add up to the downward motion. So with every single downward motion, we're going to add up more force onto the ruler, and we can essentially make the energy of the ruler go much bigger and bigger and bigger, which can essentially give us a much higher amount of amplitude. Is this possible to achieve? Do you understand what I'm saying here?
Yes, sir.
A physical জিনিসটা বুঝাচ্ছে কিনা যে what is actually happening. Now, why am I telling you this? What essentially is happening over here is that at every half cycle of the movement, we are continuously adding small amount of energy within the system. And that amount of energy addition is getting added to the system to give it a much really high amplitude. If our applied energy over here, or if our applied force over here, so if this ruler has a frequency of exactly 2 hertz, our finger also have to move at 2 hertz, but we'll be only applying force at 1 hertz because we'll be only applying force for the downward motion. We'll not be applying force for the upward motion. So we'll not be applying force. I'm sorry, my bad. Our applied force should also be 2 hertz. So once the ruler going down, we're applying force for half that motion. Then for the next half of the motion, as the ruler is coming upwards, we are not applying force. So we're not applying force over here. We're applying force over here. So we're gonna match up our hand applied force frequency with the natural frequency of the ruler for this much length, and we can make this ruler go at a pretty high frequency. It is not necessary that our hand needs to be exactly at the end. We can place our finger pretty close to the table, and we can apply little amount of force. It all comes down to the point is that how much energy are we adding in every movement. So if we add small amount of energy, we might require a bigger number of oscillation to develop a really high amplitude. If we place our finger pretty far apart, we'll be able to move our actual hand at a much higher amplitude. So individual energy added for every downward motion can be large, and we can reach to the highest amplitude much earlier. So where do we place the source is a primary determinant that how many times oscillation is it going to require to reach to the maximum amplitude, but we can essentially achieve the maximum amplitude by placing the source anywhere, because it is the purpose of the source to continuously add energy to the system, not essentially to have it placed exactly at the antinode. What is happening for this apparatus setup, if I try to get this, is that this oscillator head is placed in this position in such a way that whatever the frequency of this thing is, this oscillator has the existing frequency. So if this end of the wire is going up and down in, let's say, 10 seconds per second, 10 hertz, so it's going up and down 10 times every second, this oscillator head is also going up and down at 10 seconds. 10 hertz, so it is going in 10 times per second. So when the wire is naturally trying to go up, this oscillator is pushing it up. When the wire is naturally trying to go down, this oscillator is pulling it down. So it is adding energy in both the motions, because this is a physical oscillator. So this is essentially what we're providing in this mechanism. We could replicate this exact mechanism in this case if we were not only pressing it by a single finger. I use the example for single finger because to make it easier for understand, but rather we could actually hold it by both of our fingers, making it pinch by our index finger and our thumb. So maybe we could have both of our fingers over here and holding it on from both sides and try to vibrate it with both of our fingers. So as a result, what's going to happen, if this is our index finger and if the bottom one is our thumb, so we'll be pushing down by our index finger when the ruler is coming down, and we'll be pushing up by our thumb when the ruler is going up. So we'll be applying force in both the motions, so we'll be able to achieve the high amplitude much earlier with a fewer number of oscillations, because the rate of energy input would be much more higher. This is basically what is happening in this scenario. So placing the source somewhere, I mean, not even close to the antenna, so anywhere on the wire can achieve us to have the oscillation going up, as long as we can match the frequency. Did I answer your question anyhow?
Yes, sir.
Did it make sense what I say?
Yes, sir. Thank you.
It's not about the position, it's about, are we adding energy to the system as the system is willing to accept it?
Okay, sir. Good.
Beautiful.
Thank you.
No problem. So this was the experiment for the microwave. The next experiment that we have over here is for, we only have 1 minute left, but I would like to discuss this experiment, then we can call it a day. So bear with me for a couple of more minutes. So this is an air column closed at one end. So what is happening to this air column experiment? This is a very simplified experiment. This apparatus setup can be quite a bit different for different experimental setup. But let me show you what is actually essentially attempted here. We have a tuning fork. Every tuning fork has a fixed frequency of vibration, which is labeled in their body, and we're gonna vibrate it by hitting it on a rubber pad so that we don't damage it, and then we're gonna hold it on top of this open end, on top of this thin tube, and in this case, this much air is going to work as our air column. So the open end over here is going to work as our antinode, and this water surface is going to work as our reflector surface. This is going to be our reflecting end. So this is going to be our node. So this trapped air inside this thin tube is going to work as a one end closed tube. So what happened for one end closed tube? So what we've seen in this part of the lecture, that we've seen that for one end closed tube, we can have resonance at λ/4s or 3 λ/4s, or we can have at 5 λ/4s, so on and so forth. What is interesting is that in this case, we are not going to increase the frequency. We're going to use the same tuning fork. We're going to use the exactly same tuning fork, but by lifting up this tube up or down, we can increase or decrease the length of this air column. So what is happening? The first resonance or the first loud sound that we can hear out of this experiment can be at λ/4. The second loud sound you can hear over here, it can be achieved at approximately 3 λ/4. So how does this experiment work? We hit the tuning fork on a rubber pad, hold it up onto this air column, and then we slowly lift up the tuning fork held up on this end, not on the vibrating sides, and this tube at the same time above. Whenever we'll be lifting both of them above, for a specific height rise, you will hear that the sound coming out from the tuning fork suddenly got pretty loud. this pretty loud sound is happening because this is when this air column will be able to produce a stationary wave. As a result, it will be having an antinode on its own. So whenever there will be an antinode produced over here, beautiful thing will happen. The tuning fork will be producing its own sound by its own virtue. Simultaneously, the air that is trapped within this part of the tube, this will be also producing that exact frequency of sound along with the tuning fork. So that together they will be producing a much bigger amplitude of the vibration of the air that is going to undergo vibration over at this point, and that increase of amplitude comes out as higher volume of sound, which we can hear far out. So normally tuning fork, if you just vibrate a tuning fork, you can see it vibrating, but you cannot hear the sound. You can only hear the sound if you place it pretty close to your ears. Or you might be able to hear it if I hold it against the board. Many of you who have done my class, you have seen it, that if I hold the tuning fork, vibrating tuning fork on the board, the sound actually goes out to a much higher amount. It's all that because then the board also vibrates at the same frequency. So we can achieve the resonant at lambda by 4 air column, and then if we actually want to have the next harmonic for closed air column, which is the third harmonic, not the second one, we have to lift it up even further. And the next thing can be achieved whenever we have it at around 3 lambda by 4, not 2 lambda by 4, but 3 lambda by 4. There is a question of end correction here. End correction here, next class I'll korbo. Don't worry about this. So the first thing I'm going to pick up on the next class would be at about end correction. So we can have this thing over here at 3 lambda by 4. So this is a physical experiment that goes on showing that we can actually produce the same thing. What is different from this experiment and the drawing that I have done? In my drawing or in this discussion, I did not change the length of the tube. The length of the tube was kept same. However, by some mechanism, I was increasing the frequency of the source, which is responsible to cause the vibration within the tube. So the length of the tube was kept the same, but the frequency of the source was increased. So we had fundamental frequency, we had third harmonic, we had fifth harmonic, so on and so forth. But in this experiment, where is that? In this experiment, we are keeping the frequency of the tuning fork same. We're using the same tuning fork, so we are not going to change the F. So if you don't change the F, which means the structure of stationary wave within the tube remains the same. So if you want to have the third harmonic, you would simply require triple the amount of length. That's essentially where lifting up this tube comes in. So as we will lift up the tube further, whenever the amount of air, length of air within this tube will become 3 lambda by 4, we're going to have the next harmonic, which is going to be a much more third harmonic, which is going to be a much louder sound. So that's pretty much it for today's class. Next class, I'm going to be picking up this figure. I'll discuss this figure in detail. This is a pretty important figure for you to understand. And then I'll talk about end correction as well. And yeah, I would like to give you a small reading homework for you kids. We have the next class tomorrow. I think tomorrow, right?
Yes, sir.
For tomorrow,
Yes.
tomorrow 9:30 class, I will take this class. Don't worry about that. I missed all the other classes after 9:30, but I'll remember and take this class. Don't worry about that. I'll do that. I would like to give you a small reading homework. A chapter jeta ase stationary wave from your book. I would like you to read this chapter and mark everything that doesn't seem to understandable for you. Anything and everything. And after I am done, I'll answer your questions regarding whatever you ask me. Thank you very much. Thank you very much for the additional 5 minutes of attention. I'm closing the class today. I have another class to pick up, and see you tomorrow. Allah Hafiz.